Okay. Now, in the similar type of principles we use, we call it metallurgical balances, that is more specific to metallurgy, or I would say mineral processing, where we are dealing with large tonnages of materials, and I have to know that each circuit how much material they have to handle per unit time, and for that it is very essential to understand this. So, metallurgical balances, where are the uses? Now, steady state accounting of mass flows in a system, that is whether my system is in steady state, whether there is any leakage in the system. So, then also my mass may not be matched with your input is equal to output rate. Not many situations we encounter with the decay, but accumulation is there most of the cases, but chemical reactions hardly take place and we do not even consider in our mass balances. They may be occurring, but we say it is a physical separation, but we do not take into that into consideration, but accumulation is common. And we can identify that whether there is any accumulation, unwanted accumulation anywhere. That is, how do I know that my pipeline is going to be choked? Because when my mass balance does not match and I see the rate of accumulation has gone up into the pipe, so where it has gone? It must be getting settled into the pipe system. So, my pipe may be choked immediately. So, I can basically stop my production and I can check it physically, look at the operating conditions, what is happening, all this. Then evaluation of metallurgical test work, like I said that I have got 1% copper, but I am processing 5000 tons per hour. So, I can always basically trace that how much of metal I will be getting out of that 5000 tons per hour, because say suppose I want to produce 200 tons of copper per unit time. So, how much of basically material I have to process, then I know in a processing I have to discard something, I will be having losses. So, that is your first equation what we discussed, that is contained value should be greater than is equal to this how much you are getting plus losses plus all this. Okay. So, how do I know how much is the losses, okay? And how do I size my equipment, that what will be my sizing of my crusher, what will be my sizing of my, say suppose cyclone, how many cyclones I require, suppose magnetic separator, what should be the capacity of that magnetic separator, if I do not know that how much is going there. Another good thing is that about mass balancing, why it is essential, that is, say suppose I am getting 200 tons per hour of metal to be handled or 2000 tons per hour, that only my mass balance will tell me, that is how much is the available material. So, if I am having 1% of my copper in my ore, if I am processing 5000 tons per hour of my mineral ore, so theoretically how much of copper basically I am transporting, and after each stages, that is how do I know what is the rate of concentration. So, how much I am throwing it, I am unable to recover it at each different stages, because I have got a series of operations. So, how do I track it? I have to track it by zone wise mass balancing. So, if I am losing most of my copper, the majority of my copper which it should not at one go at one unit operation, then I have to optimize it, I have to recheck it, that what is the problem with that, then I can find out the faults of that unit operation and I can redo the things. So, otherwise I cannot say identify them. Then comparison of two different mills or circuits, how do I compare? Suppose I have got two parallel circuits, okay, or maybe that is in the your laboratory I want to test. Suppose I have proposed you that it is the better processing route, that you process it through this is my flow sheet, you will get a better concentrate grade and recovery, because the quality and quantity both are important, because my value lies on both, how much, what is the quality and what is the quantity. And he proposes me another circuit, and how do I know, how do I compare that, okay, we both of us have processed 100 tons of material, out of that in my case I have recovered 20 tons of that material of that specified grade, but he has recovered 22 tons of materials of that specified grade. So, that means his circuit is better than this. So, how do I do it? I need to do the mass balancing, okay. That is your metallurgical, that is why we call it metallurgical balance. Process control of an operation plant. In a process control, what do we measure? We measure either the flow rates, that is what we discussed, that is QS, CS, or maybe in situ CS, that what is the concentration of that particular element, or maybe some other parameters, that is, say, suppose what is the pH of my water. So, again my water is getting diluted by some other materials, whether my pH is remaining constant or not, how much of water I have to add, fresh water I have to add to reduce the pH, or maybe how much of alkali I have to add. So, how do I know, how do I quantify? So, I have to do this mass balancing for that, okay, for many purposes. Properties of the balance require samples for assay and weights oblique flow rates. That is, again many times I have to do the assay analysis. You know what is the meaning of assay? That means what is the, suppose iron content, okay, I am processing iron. So, what is the assay of iron ore means how much of Fe is there. That is my assay, that is my your wanted material, how much, what is the percentage of that, that is, or in another way I can call it grade also. But grade is basically the in totality, that is how much of iron is there, how much of impurity is it there. So, grade is basically more of user driven, that is what is the user specified, but here assay means for that particular component, that element I am interested in. Okay. So, require samples for assay. So, I need to have your this analysis, unless and until I have got on stream analyzer, I have to take a representative sample, and that is where the sampling is coming into big way. That is, if my sample is wrong, so then my assay analysis, it will lead me to a different mass balancing, and my entire calculations will be wrong, and entire process, your optimization strategies or whatever you do, that will be wrong. So, the error is coming from sampling. Okay. So, you have to be very careful. Accuracy of the assay is used, there will be inaccuracy in that, but how much is the accuracy, what is the confidence interval, how much is the standard deviation, I must know that. Then turnaround time of the assays, at what interval, that we have already discussed in during sampling. Now, what are the methods for this? The method relies on equations similar to the conservation of mass again. Now, say suppose this is my one unit where I am separating my mineral, I am upgrading it. Okay. So, this is my feed material, any element, it could be any mineral, I want to upgrade it. So, when I have basically used, say, suppose a gravity concentration or maybe some other technique. So, I have concentrated this component into one group, that is basically the C, say suppose that is we call it concentrate, and another one is tailing. So, a simple mass balance is F is equal to C plus T, but that is on overall mass, that is how much I have fed into that system, how much we are rejecting and how much we are recovering as your valuable material. Another mass balancing is that is what is the grade of this, of my interest. So, suppose I have got an element, why I am processing it? To upgrade it. Upgrade what? So, suppose it is copper. Now, in my feed material, how much is the copper percentage? So, that I can denote it by the fractional concentration of that, that is your F, that is your small f, C and T, I can say assay of each respective stream, that is the copper percentage in each respective stream. So, what I would expect, that if there is a basically upgradation, then my concentration of copper in capital C, that is this zone, that is your concentrate, should go up, and when it is going up, what you are throwing out, that should be less, but the total mass, it has to be conserved. So, the concentration here has gone up, means I have discarded more of unwanted material selectively from here, which has gone there. So, my mass of this fraction has to be less than this, otherwise I cannot do that. Otherwise, the many times I have seen that people say that what is the recovery? Recovery is 100%, does not tell anything. This material is there, I wanted to separate this one, but I have not done anything, I have just brought it here. Recovery is 100%, but I have not done any upgradation. So, I must tell what is the grade, that means what is the percentage of this and this total volume, and how much is the increase in my concentration of that in particular fraction. So, when I want to increase the concentration of this portion, suppose I chop it from here, so that means its mass will be much more less than the total mass. So, where it has gone. So, this has to be balanced. Okay. So, I can balance it with this, that your F is equal to C plus T, that is the total mass flow rate, and I can also go by the element wise, that is my assay of one element, that is FF is equal to CC plus TT, correct, no problem. Now, how do I use this two product formula in calculating some of the situations, okay? Like, so I have got 6 variables basically, capital F, capital C and capital T. I do not know how much you are feeding, how much is basically going into the concentrate, how much is going into tail, and then what is the relative percentage of that element 1 in, that is your small f, small c and small t, okay. So, these are basically the species analysis of my interest. So, I have got 6 variables. So, cleverly we can reduce it into 5. I say that f is equal to 100, whatever it is, 100 can be equal to 100 tons, 1000 tons, 500 tons, 1 ton, 0.1 ton, anything. So, just for simple mass balancing I say that is equal to 100 unit. So, I can reduce the number of variables to 5 now. Now, what I have to do? Now, I have got 5 variables. So, obtain the value of 3 variables. So, when I have got 3 variables, I can solve for others. That is, do I need to measure all the 5 values? That is the question. If you do that, that is very good, but most of the cases why to waste time and money for measuring all the streams, all the values, all the 5 units. So, if I want to measure, I will measure the other 3, and by using equations I can solve for nothing. That is what is the basically this exercise is, okay. So, how do I do it? So, the calculation can be done using the formula. You can write a formula or by simply filling in a table. I can have a table that is like your, I will show you what do I mean by table, you know, like your Excel spreadsheet you can do it. So, F, C and T are the 3 measured variables that the formula is used. Like most of the cases, you know, when you have on stream analyzers, and if you are able to measure that F, that is your small, that is the assays and in respective streams, and with some statistical deviation which is basically acceptable to you, then you can simply use the formulas, okay. You do not need even the tables. If other variables are given, then the table is simply filled in, like I want to know the values of others. This is what the example I am trying to show, okay. So, two product formula I can write based on those equations, F is equal to capital F is equal to capital C plus capital T, and FF is equal to CC plus TT, and by simply rearranging them I can get a formula for C, capital C is equal to 100 into, remember here there is no capital F and no capital T, it is only based on the grades of that is your assay analysis, F minus T divided by C minus T, and simply I can also, if I know the C value, I can also calculate the T in the similar way, and if I know C and T I can get back to F, okay. So, this is what I am saying, that if I have on stream analyzers I can simply use that. And what is the percentage recovery? Recovery means how much of that I had in my element, that is my feed element. So, suppose it is 100 unit, I have got 10% of that, that means 10 units of there, and then I have recovered 8 units in the underflow, 2 units are going to the basically the overflow. So, what is the recovery of that element in underflow is 8 by 10 into 100, that is 80%, and likewise in your, what is the recovery of that element into tailings is 20%, 2 by 10 into 100, that is 20%, okay. So, the metallurgical balance table is, so recovery I can write it 100 into C into F minus T divided by F into C minus T, and these are all small. So, basically you can derive it, if you I rearrange those equations I can easily get that. Now, so I can arrange a table like this and you can deduct like that. Now, I will show you this table, okay. So, I will show you that how if you can make a basically a Excel spreadsheet like this and how you can solve. Now, so suppose you are given the following 3 variables, that is all assays, okay, like by some means maybe your on stream analyzer, maybe your say by sampling and doing it in the laboratory you get the basically the assays of the 3 streams, that is your feed, concentrate and tails, that is I know the copper content of that. Okay. Now you see that, say suppose that is in my feed, that is in my concentrate, the percentage copper is 26.9%, then my tails it is 0.072%, so and my feed it is 1.29% of copper. So these three values are given, and what is the another known value I can use, that is weight percent of my feed is simply I can say 100%. Now you see the rest of the columns I can fill it up by using those equations. Okay. So first thing what I can do, that is what will be the basically the capital C, I can calculate it C by using this formula, that is F I know 100 and these values I know, small f, small t, C and small t I know. So I get a value of C. So what is the C? That is basically the concentrate weight percent, that is 4.54 weight percent of that out of the total feed. So when I know the feed is 100 and this is 4.54, so how much is going into the tails? 100 minus 4.54. Simply I can calculate that. So that is 95.46. So I got the values. Okay. Now I have to calculate the recoveries. So for recovery, you know, that is the simplest way is to convert into copper units. It does not have any physical meaning, but just for calculation purposes, for simplicity of the calculations. That is, I can convert them, that 4.54 multiplied by 26.9, how much is copper unit going there, and how much is there, that I can calculate, that is 6.873, and here this is basically 128.99. So now if I want to calculate that how much is the recovery of copper here in my concentrate, okay, you are having some doubt about it. So this is the weight percent, that is how much is the quantity getting, what is the basically the grade, that is 26.9. Now but just for simplicity of calculation, it does not have any physical meaning, I am just converting it that how much is the copper unit. So 4.54 minus multiplied by 26.9, so I get this value. Okay. Then like that I am getting all the values here. So I can calculate the recovery of copper in my concentrate. So I have got this in my feed, out of that I have recovered this. So it is 122.126 divided by this multiplied by 100 will give me the basically the recovery of my copper in my concentrate, it is 94.67%. Okay. As a, if I get it, then I would say that it is a very good separator. Okay. Then similarly I will get my tailing recovery, it will be 100 minus this, because the total recovery has to be 100%. So I will get 5.33, and so there I can put it like this. Now if I say that my feed rate is this, suppose that is the tonnages I have to produce this at this rate if I have to process, or say suppose I want that this much of copper bearing minerals of this quality I want per unit time. So I can back calculate how much should be my feed rate, because I know the recovery and all this. Now say suppose I give a value of 25,000 tons per day I want to process. Okay. So what will be my load on my concentrate stream, what will be my load on my basically the tailing stream. So now I can just multiply them with these fractions, that is what is the what percentages of this. So I can get these values. Now this is very essential to get this. Now you see the implications of this. Now what it is telling me, that the concentrate from a material handling point of view, what should be my load on my bulk material handling. So this is per tons per day. Okay. Now say suppose I want to transport it by through a conveyor belt. So what would be the capacity of my conveyor belt? I can divide it by per hour basis, per minute basis, depending upon the design. But in case of tailings, you see that the load is much more higher. Okay, that is much of material I have to handle. So the design of my concentrate stream, that is the bulk material handling stream, and my design of tailing handling stream is entirely different, because I know now that how much of tonnages I have to produce. Okay. And not only that, even when I get the tonnages of this material, now I have to transport it, say suppose up to the, suppose this is my final grade. Now this is what I will be selling it. Now I have to transport it to a 100 kilometers or 500 kilometers distance. So now I can calculate that whether I will, basically I can decide that whether I can transport them through pipeline or maybe through trucks or through railway wagons, and how much will be the load on that. So if I want to transport it by railway, so 1135 tons per day is not much. So how many rakes you require? Okay. So suppose I have got your 59 basically wagons, which is called a rake. I don't know 59 or 58. I get confused always. 58, no? 59, then it is correct. So I know that what is the, each wagon, what is the volume? I know the bulk density of this material. So should I plan to dispatch it every day? Because I am having only 1135 tons. So it is basically not having any meaning. So what I can do? Now where do I store them? So I have to have a storage place. What will be the rate of accumulation in the storage place? When I will dispatch it? So your entire bulk material handling system, that how much of material I have to handle, then whether I should store it into open air, then what is the angle of repose and how much of quantity of material. So entire decision on your design depends on that, how much of material you are basically handling. More on that is tailings. What I am going to do with this? Huge quantity, 23,000 tons, 23.8 thousand tons per day. What I am going to do with that? Whether I will send it to a tailing pond, how do I send it? Is it through pipeline? Is it through truck? Is it through some other means? Is it through conveyor belts? So what are their conditions? So all these decisions I can take, okay. Or whether I have got, instead of copper I will also have lead or zinc or something. Now say suppose the next stage I want to concentrate my lead. So I start with 25,000 ton of your copper mineral, but I have got some other valuable mineral in that, that is your maybe lead, zinc, your sometimes your say some other materials like your cadmium, mercury, okay, it is not mercury, it is basically the silver, okay. Sometimes you may get gold also. So then if I am sending this one, so it is not the load on my next processing circuit, it has now reduced from 25,000 tons per day to 23,000 say 865 tons. So like that I can select my basically the processing equipment sizing, entire thing, entire circuit, the capacities I can select based on this. So this is the heart of the mineral processing equipment designing part, and this type of system you may get this type of material handling problem you can get all this detailed information in any other industries like your food processing industry, like your agriculture industry, like your handling your large tonnages of material, and in between you want to basically size them, and then each size fractions you want to apply it for different purposes, okay. Like your rice grain, if it is basically all basically say unbroken part, you get a different value. If you have a broken part, you have got a different value. If you have got some other impurities, that does not have any value, but how much of that it is there, how much per unit time I have to handle, that is only by mass balancing you can do. Another good thing is that this is idealistic situation at F is equal to C plus T and all this. So we have assumed that there is no losses, but in actual case if I want to do it in any plant, you will find that these are not balanced. So what I can do, I can find out. Now I can go for each units and I can apply this and I can find out where I am losing that material, whether it is avoidable or whether it is unavoidable. There will be some kind of accumulations also, I can calculate all this. So this is the benefit of doing mass balancing. I will show you some more cases, like given the following 4 variables like product weights and product assays. There I have given all the assays of all the materials. Now I have now given product weights and product assays, like say I know this is my concentrate weight, that is 45.3 grams. Suppose I have done a laboratory test, tailing weight is 952.1 grams. So I can calculate what is the basically the say actually all the feed, but before that these are the given data. So, these are the product weights and given, and these are basically the product assays given, percentage copper and all these values are given. Now, how do I calculate? So, this is the weight, I can convert it into weight percentages and then I can fill up all the basically the unknown variables, what will be the values for that. Okay. So, like that I can get all the values, and you have to check that whether they are getting balanced or not, that means whether every row and column they are getting balanced or not. Then I can have different systems, like I may not be able to get the assay value always. I may not have online on-stream systems, or maybe I am not having access to get a representative sample from that place. Many times it occurs. Suppose one unit is there and it is going to another unit where we will get the sample. Okay. So, that time you are available with, say suppose the percentage recovery values are given, percentage copper in concentrate, because that is the end product, you can always measure that. I can always measure the percentage copper in feed also if it is possible, and so quite doable many times. Okay. Then tailings I am not able, because that tailings I am sending it for recovering other minerals for further processing. So, I cannot get a sample from the tailing point, say actually tailing end for this circuit. Okay. But there I can calculate the recovery of that, that is the recovery I know. So, then what are the known values? I am given these values. So, now I have to fill up the other things. Okay. So, I can do again using that formula, I can get all these values easily, that is in this sequence. So, this is the beauty of creating an Excel sheet, and if they are linked with formulas, and you can solve these problems, and once you have set it right, you have to forget. If say you can forget the formulas easily, then you are getting the numbers done. And then if I am given the basically the feed rates and all this thing, you can calculate. Okay. So, now the method relies on basically the metallurgical balance, but many times I may not have only your 2 product system. I can have 3 product system, I can have n product system. Like n product, how we can get n number of product, because if I have n number of species and which are all basically important, like beach placer mineral, I said that you have got 5-6 different wanted minerals. Everything is important. I want to do balancing for each element, and I have got your 5-6 different unit operations. So, how do I know which unit is inefficient, which unit is efficient? So, there I can say the end product, there basically you have to do some kind of your coding, you have to write, and you have to take adjusted weights and all this, that is your weighted adjusted values, you know. But I am just showing you that is how you can do the iteration type of analysis even by using this 2 product formula for a 3 product system. Okay. Like suppose I have got a feed, and then you have got first unit operations, you are getting concentrate 1, and the tailings, it is going into another section like a froth flotation system, or maybe 1 unit that it is going, you are getting a concentrate 1, but tailings you are still having that material, I do not want to throw it. So, I am sending it again to another separator where I am getting concentrate 2, and then finally I am throwing it out. So, now I have got 3 products C1, C2 and T. So, what is the equation now? That is F is equal to C1 plus C2 plus T, correct? And if I go for the balancing based on your species wise, I can say F1 is equal to C1 C11, because I will be having some grade of that here, then I will be having some grade here, that is C21, and I will be losing some of this material also there, that is T1. And F2, say suppose I have got another product, that is I have got lead and zinc both. Okay. In one go I want to recover, say suppose copper I am targeting, but with that I am also recovering some kind of zinc. So, that is a contaminant, but that is unavoidable, that I have to take care next stage, maybe in the refining stage. And here I want to concentrate more of zinc, but still I am having some kind of copper. So, there are basically 2 species, that is why I can, it will be more complicated if I have n number of species. Okay. Then you have to solve it in a matrix form. So, FF2 again I can balance it with these equations. So, I think these are all clear. So, C1 and C2 are basically concentrate 1 and 2 tonnage or weight percent, T is equal to tailing tonnage or weight percent, and F1, C11, C21, T1 these are basically stream assay for element 1, whatever unit you can put it, okay, that is immaterial. Now, see that how we can, whether we can apply two product formula here or not, little bit tedious, little bit of iteration, but yes we can. So, what we can do, and is say suppose I am giving now the values, okay. The F1 that is in your feed, the copper percentage is 1.29% copper and it has got 4.32% of zinc, okay. Now, in the first unit operation I have done it, and finally, whatever I am getting the tailings I have got 0.072% of copper and 0.32% of zinc, that is what I am throwing out. I could not recover it, that is inefficiency of my process, okay. And C1, after this concentrate what I am getting, there my objective, there my focus was to concentrate more on copper, but some zinc has also come. Then the next step I will probably think that what do I do with this copper and zinc both, I cannot put it into a furnace, I cannot melt them. So that is a different issue, that how do I get rid of that, but for mass balancing I am saying here I am getting 26.9% copper, so that has been enriched from 1.29 to 26.9, but I am also enriching zinc also from 4.32 to 9.25%. That is mostly it happens with the flotation processes, because whatever chemicals you are adding, they may be actually upgrading both the minerals, like your zinc could be sphalerite, ZnS, copper is basically the chalcopyrite. So those are so actually both of them are sulfur bearing minerals. So if you are adding some reagent, okay, normally MIBC or that type of reagent you are using, so when it will start floating each one, but you try to depress zinc so that I can float more of that, but that is a flotation process, that is a different one. But this is the scenario here, and the C2 where I wanted to concentrate more of zinc, here you see that I have got 57.7% zinc and I have got 1.1% copper. Now 1.1% copper, it may look very less, but you look at the feed grade, that is 1.29%. So that is also quite high grade of copper I am losing there, okay. Now what I want to do, that is, but I do not know how much is there, how much it is going there, okay, that is basically unknown, and I do not know what is the quantity of material I am feeding, okay. So how do I solve this problem? That is what I am trying to show you, that is two product formula to solve in stages. So what are my unknowns? I do not know that what is the material balance there, how much of material is going where, and here how big should this cell be, because I do not know how much of material is going there in terms of even percentage, what is the percentage split, how much I am getting it in concentrate 1, how much of material. So how much of material it has to handle here, that I do not know. So what I do, we need the assays of the intermediate product T1. I need to know what I am feeding into the second unit, what is the copper percentage and what is the zinc percentage there, okay. That is what I want to solve. So what I can do, that is your step 1, that is FF1 is equal to C1 C11 plus T1 T11, that is for this node, that is we call it node. So I can write an equation for this, and I can also write 100 is equal to C1 plus T1, okay. And for node 2, that is for this node I can write T1 T12, I do not know the grade of that second element, is equal to C2 into C22 plus T2, and T1 is equal to C2 plus T, that is for this node I have written, okay. Check that the assays of element 2 in circuit 1 are balanced, check that the assays of element 1 in circuit 2 are balanced. That means what I am saying, that is check whether the zinc is balanced in circuit 1 and check the balance of copper in circuit 2 whether that is balanced, okay. So what I can do, I can go for that type of, again the first step will be, that is the formula, and we can write this again create this actually spreadsheet type of thing, and we can say that this is the given values, that is C1 is 26.9%. I am now putting it in this form, and your this is basically 0.104, that is T1, that is T1 is 0.104. Here I have just balanced it using that equation, but I am getting these values, that is T1 is equal to 0.104 and T12 is equal to 4.15%. That is why when I am separating the nodes, but in totality it must be balanced. So, I must check that whether the entire thing is balanced or not, okay, because I have discretized it. But when it is working in a continuous mode, I must check that whether they are balanced properly or not. So, this value I have given, that is your T1 is equal to 0.104% copper, and basically you are giving F is equal to 1.29%. So, that is what I am getting. Okay. So, now I can solve, that is all the 3 assays I know. Now, let me check that what are the other values and whether they should match, whether they are matching with the values given for others. Okay. So, I can put F is equal to 100, and then so C1 I can calculate based on that is the formula. So, I can get this is the C1 is equal to stream 1, that is your 4.4268%. So, my T1 should be 100 minus that 95.574. So, what will be the recovery of that? I can always calculate, that is that using that same formula what we have used. Now, this is what I checked it for this, but I have not checked the actual thing, that is that let us examine application of the two product formula. So, I have got these values, and let us see that. Check assays of T1 balance, that is whether T1 is balanced or not, because I have given these values whether it is balanced. So, what I can do, that is zinc assays in circuit 1, but I have balanced it on the basis of copper. So, if my mass balancing is right, because the similar material I am basically say actually that processing, so then my zinc also should be balanced if my mass balance is correct. So, I can again go for that, the similar type of sheet, and then we are basically looking for those values, that is C1 is equal to the percentage of zinc is equal to 9.25%, that is what I have got it here, and then your F is equal to 4.32%, that is what I have got, and then I can calculate that what are the zinc units here and what are the zinc units in my feed. So, I can calculate how much is the zinc unit in basically T1. So, I can back calculate that what will be the percentage of my zinc here, 4.092, but here you see that it is T1 should be 4.092, but here it is 4.15%. Okay. So, that means it is not properly balanced. So, if my mass balance was right, then the zinc content at T1 should be 4.092%, that is why I have given a bracket that you look at it, and it is 4.15%. So, I have to iterate it unless and until all the elements are balanced, okay, so that I can use this two product formula. So, I can get these recovery values, that is fine, but it is not matching 4.092 with that. So, what I will do, sorry, so the zinc assay of T1 must be adjusted by 0.058% of zinc. So, that is your adjustment, that is you have to replace that value with this new value 4.058. When you have done it, again you go back to your mass balancing for your copper, that if I use that whether it is getting balanced, otherwise unless and until you have to keep doing it unless and until the entire thing is balanced. So, what I have to do, second step, that I can write T1 T12 is equal to C2 C22 plus T2, and so I have to check that whether this is balanced. Now, I have changed it from that value. So, it is now 4.092% zinc. Now, let me check that what is the C2 here. Okay. So, C2 I get the value from here, and I write it that it is 57.7% zinc, that is given here, and then this is 0.342, that is your T, that is what I am getting here, and then I can calculate what is the T1, that is your, so basically measured one, that is 4.092. Now, whether this value is correct or not, that I am checking it with another node. What value I have got? By mass balancing it by the first node, that should be balanced in the second node also. If they are not, that means again I have to redo it. So, when I do that, it is the percentages I am getting like that, because I know again the 3 assays I know, I can easily get back to that. And look at these values now, that it is now 391.12, and whereas I am getting 90.530, I can put it in place of 90.537 for my simplicity of my equations. So, with respect to F, that is basically 4.32% zinc, that has to be. So, what I do, that is check assays of T1 balance now. I have done it for circuit 2, come back to circuit again, circuit 1 again. So, copper assays in circuit 2, now you see that these are the values given. So, you check how much is the percentage copper, that is given 1.1%, and your T is equal to 0.072, that is the value of this, it is coming, and then copper units I can convert it, and then we can calculate that what will be a T1, that is percentage copper, that is 0.139, but what it was earlier. So, T1 it is basically giving you 0.072, but here it is 0.139, okay. So, that is that is a T1 here. So, T1 is the, what is the copper percent? 0.104, but you are getting 0.139. So, that means again it has to be adjusted. So, I can get the recovery values. So, the copper assay of T1 must be adjusted by plus 0.035% copper. So, you have to now change this, now this value again changed, now it is 0.139% copper. So, basically it is like your 2 product formula I am using, because I am not using the entire formula for 3 product, that is why this is the problem. But if I want to use the entire 3 product formula, my calculation length may go up, and if I have n number of products, there I cannot use this 2 product formula, because I have to, my time for calculation will be enormous. That is why you need softwares, that is why the mass balancing softwares are in use. And most of the cases, when you are measuring the data, you are not getting perfect balance, it is not perfectly balanced. So, how much of adjustment I have to do, that depends on some kind of your weighted average methods, that is what we discussed during sampling. So, we have to take weighted average values, we have to calculate the sources of errors and all this, that I will discuss. So, now I have got these 2 values, still we are not sure that whether they are balancing or not. So, again I can use this to return to circuit 1, I can again come back to this, that whether they are balanced, if they are correct, then let us check it in the similar fashion. So, let us do it quickly, and we are getting these values, okay. So, instead of the old values, I am now using the new values, okay. Now, you see that what is happening. So, this is what is somewhat we are getting the balance. Now, what do we have to do? We have to check it, the recheck assays of T1 balance by using the second node. That is what I have to do it, that the zinc assays in circuit 1, that is for copper I have done it, whether it is balanced for zinc, because then only I will say that my mass balance is correct. Now, again for zinc I will try, and I will use these values, and I will see that whether they are getting balanced or not. So, again you see that it becomes 4.098. Now, it is again not matching with that, it was 4.092, but now it is showing 4.098. So, that means there is some problem with the balancing again. So, what I have to do? Again I have to readjust this value with that 4.098. So, I will put this value again, and I have to keep doing it unless and until they converge, okay. And when you are checking for node 1 for element 1, you must check the element 2 for node 1. When you are confident about this, then you check for node 2 the element 1. If it is element 1 is balanced, you check for element 2. If they are not, again you start with node 1. That is what you have to keep on doing it unless and until they are balanced. But remember it, for plant data it will never be balanced. So, do not worry. So, there you put the standard deviations, okay. There you put the tolerance limits, that my balancing means does it really have to converge properly, or like your iteration, you put that this minus this is equal to 0 is the ideal case, but if you ask for a solution for that definition for convergence is y1 minus y2 is equal to 0, if you put, then your computational time shoots up, and then probably your code also gets confused that when I will get a solution, you may take enormous amount of time. So what do we do? Instead of putting 0, we say that fifth decimal point of 0 and then 1, that is 16 digits or something after that. So it is very tends to 0 but not 0, you get a quick solution. Okay. So this type of practices you have to keep on doing it, and unless and until they are balanced, and this is a little bit tedious, better to write codes, to get a solution for this if you are really interested in knowing. See how many times I have to do it only for 2 nodes, and you see that even for a flotation circuit there will be at least 3-4 different cells, and then you think of now starting from your screen and then crusher, different types of crushers, then you have got different types of separators, and if I want to do mass balance for the entire plant, at least 50 units will be there, and then it is very tedious job, and that is a must if I have some process disturbances somewhere. So before I say that I am not getting this product quality or the quantity, it is called basically the plant auditing. So in the plant auditing, the first thing is that take the representative sample properly, that is your sampling becomes very important case, and then you do the mass balancing, and then your mass balance by unit wise, that node wise, and then you identify that where I am having the inefficiencies, then only you can identify, okay, the problem is with the cyclone, the problem is not with my flotation cell, but the problem is with my cyclone, or otherwise you may say the problem starts from my crusher itself. So how do I identify? So that is called the fault finding, that is how you will get to know. Like simple thing, like if I have body temperature which is more than my say comfort level, suppose it is 103 degree Fahrenheit, then I go to a doctor. Initially what he does, if it is a good doctor, he will give me just simple paracetamol, because if it is the first thing is that there could be a viral attack. So viral, there is no medicine, so you have to wait for 2-3 days unless and until they go out of my system. After that again, after 2-3 days I go back to the doctor, there is still fever is coming, and fever is an indication of some problem. This could be starting from your cancer to just simple viral attack, it can be anything, your body temperature going up. So your metallurgical grade is not up to the mark, or maybe quantity I am not getting, that is only an indication of some problem somewhere. So first thing is that initially I will say that okay, there may be some unsteadiness because of somewhere some problem. So let me check the data for a duration of time. So what is the, have you given that time before you jump into conclusion that whether I am getting inconsistent product quality. So what is the standard deviation of that in the inconsistency? Otherwise you may end up paying money to the consultants unnecessary, okay, and you may be inviting more trouble. So after that you go for some tests, the doctors they say okay, we will test for typhoid, we will test for malaria and all sorts of things, and even though you are not getting anything but still your fever is not subsiding, then you will go for much more detailed analysis, that is you do the X-ray and all sorts of things, like that type of investigation we have to do. That is what we call plant health auditing when I have this, but this culture is mostly not being practiced in India, but in other mining companies like your processing say your circuits, it is very common that you do health auditing, okay, and health auditors they first perform this task, sampling and then the basically mass balancing. Without that you cannot identify where is the problem, okay. So like that it is you are basically continuing, and finally basically you are applying that again and you are getting all these values finally, and then again you recheck it that whether my mass is balanced or not by applying 2 product formulas. So difference between 2 product and 3 product, now I will show you that I can also apply, that is your 3 product formulas directly also, and my circuits could be configured like this, that is my feed is coming like this, you have a bulk concentrate, tailing goes out. There basically tails is after second node. Here it could be from my first node, and then here bulk concentrate, I will have C1 and C2 both are important to me. I am not throwing out anything. So, again my mass balancing equations I have to rearrange, okay, applying the same principle, but it will be the different types of thing. Now, if I want to use a direct 3 product formula with that concept, I can devise that. Okay. How do I do it? Now, feed is equal to concentrate 1 plus concentrate 2 plus tailing. I have got 2 concentrate. Okay. Now, the total mass F is equal to C1 plus C2 plus T. So, that is your 4 unknowns here. Now, element 1 FF1 is equal to C1 C11 plus C2 C21 plus T T21 plus 4 unknowns here. Addition to that, we are adding another 4 unknowns. Element 2 FF2, that is for element 2, and then you can add another 4 unknowns here. So, I have got 12 unknowns. Okay. F is equal to 100, so I can deduct 1 variable. So, I have left with 11 variable. So, how many variables I have to measure? At least 8 to get the mass balances. Okay. So, I have to have measurements. Now, whether I will have on stream or off stream, that is a different issue. Okay. So, and then if I have to solve 3 unknowns values, we can easily solve them, and these are the formulas for 3 product. Basically, the simply based on that concept, the C1 is equal to 100, and you can derive it, you can try it. Okay. This will be a good exercise tonight for you, and you can show me tomorrow whether you got this formula or not. So, C1 is equal to 100, but please do not Google it, you may get it from somewhere, but you try it on your own for your better understanding. So, 100 F1 minus T1, and you see that these are all basically based on grades, you can get it. That is the what is the percentage of C1, and C2 also I can get it, and T I can get 100 minus C1 minus C2. So, these formulas I can use it even for 3 products, and then your 3 product formula, that is what I am saying, that when I apply it, you may say that Professor Majumdar has taught a wrong thing. I did it for my plant, but it is not getting balanced, but it is not my fault, it is simply derivation of your equations, but your plant conditions, I am repeating, it will never be balanced. Okay. So, you have to ask that how much of tolerance is applicable, and then how do I bring it to as accurate as possible. Again I will come back, the reason an inaccurate answer may be obtained is because of measurement errors, and majority of them are coming from sampling. So, that is the propagation of errors is very, very important. How did I sample it? Because these are all basically slurry samples. Now, you probably remember that the material is flowing through a pipe, and if I put a hole outside, and if I am just taking a part of that, and if I want to do mass balance based on that, it will never be balanced, because you are not cutting the entire stream. The concentration of copper and zinc may be different at that place, and if I take an average value of that. So, never do that, try to cut the stream. So, these are the basically the importance of sampling. Then sample preparation, that is, even in the laboratory I said that how did you do it, because if you are analyzing in the laboratory, how did you prepare the sample, how did you ensure that there is no contamination, there is no evaporation losses or something like that. Then your contamination, then non-steady state conditions in the process during sampling. These are all basically mass balancing we have done, assuming that my process is in steady state. But how do you check that whether your entire plant is running in steady state? Can you answer me? Very simple way to look at that whether it has reached steady state or not. What is steady state? So, you just simply take the samples from any stream, okay, and you measure some, say your slurry flow rate over a period of time, and you see that whether the flow rate is changing over time or not. Okay. And even if you want to make sure of that, that volumetric flow rate may be matched, but you may dry that sample quickly and see that whether my mass flow rate is changing or not. If you want to make sure more of this, I can do the size analysis of those, and you see that whether my size analysis is changing, that is the right kind of your basically the way of knowing that whether my process is in steady state, because if my size distribution does not change, if my assay size by size assay does not change over a period of time, that is I have got 5, 6 different samples of different time intervals, and if they are not changing, then only we can say that my system is running in steady state. Again, in actual plant conditions, you may not have actually the steady state conditions. If you say that what is the time domain, steady state is basically we are dividing it by time, but what is the time domain? If you say that in a even in a microsecond scale I want it is in steady state, you will never get it. Even in per second basis you will not get it, but over a period of time, say suppose per hour basis, probably you can get a steady state, because you are dealing with heterogeneous materials. So, the pumping, there will be some inconsistency in the pumping, there may be a voltage fluctuations, there may be some kind of settling somewhere, you know, and then you cannot say that well my system is not in steady state, so I cannot do the mass balancing. What do you have to do? You have to apply some statistics, you have to apply some statistical way of filtering the noises, and then you see that with at 95% confidence level with an basically acceptable standard deviations, whether I can consider the system as basically steady state. So, the mass balancing involves a lot of statistical calculations here, statistical analysis here. The what I have discussed, that is only a simplistic form of that mass balancing, is much more tedious than what it is. So, analytical lab results are usually very accurate. Mostly, if I have a trained manpower, if it is a calibration type of equipment, and if I am repeating it again and again, and if that gentleman is analyzing only iron for last 20 years, so very less chances of having measurement errors, if the equipment is also good, if my trained person is good. But most of the errors as basically, although mistakes do occur and strange assays can occur, but sometimes there is a calibration problem, something wrong with the basically with the machine, then you may get some kind of, sometimes it may be misreporting, 56.8% reported as 65.8%, quite common. So, misreporting, and then you are basically doing all kind of calculations based on 65.8, whether actually it is 56.8. So, you have to be careful about that, and that is why basically this all this your standard, they say that standard protocols like your ISO standards, they say that documentation and it should be verified. This is what I also practice with my students, even PhD students, that when you do an experiment, I will not check your Excel data. If I have some doubt, I will look at your basically the register where you have written down the weights of the samples in your hand, and there should be a date that this day who has done this, what are the sample weights, and these sample weights, these samples are kept in polythene bags. There must be a tag, and in that tag you write that this is the reference number of the register page number, this day it was done and this is the weight. Now, suppose there it is written 1150 grams and your register also written 1150 grams, then when you are transferring into Excel, many times it happens it becomes 1511 gram, and then your percentages and everything change and you start thinking that I have invented something, it is not. Okay. So, do not so there should be basically check and balances at different places. So, then your metallurgical balance, process disturbances leading to variation in results, there could be many reasons for your assays are not balanced, your mineralogy, your ore is changing. Okay. So, this is quite common. So, mineralogy changes, that is your quality and quantity also change, because entire thing is dependent on physical separation processes. Okay. They are sensitive with this. Liberation size changes, that is locked characteristic, that is I have assumed that my entire material will be liberated at below 40 micron, but in this case it was liberated below 30 micron. So, my responses of the beneficiation methods, the responses would be different. So, I may be getting different type of assays at different places. Okay. So, I may have basically noises because of that, but they are not noise, they are real. Particle size changes, coarse and ultrafines. like the sample has become little bit friable. So, what is happening during delivery, during handling, there is some basically changes in their size distributions. So, I can have this problem. Water chemistry changes, very common, because I am recycling the water. So, when I am recycling the water, what will happen? I am not basically recycling the, I am not taking out all the darts from there. There will be some suspended material, there could be some dissolved solids, and when I am recycling it again and again, the water chemistry changes, the pH could be changed, the suspended solids could be changed. So, the inaccurate mass balances could be because of pH and ions and all this, the factors are there, water chemistry changes. Then process control of flow rates, like I have got a flow rate measurement devices, but have I calibrated it? Do I really believe that value what is giving? Okay. So, when did I last check it? So, you must look at the calibration problems, because the flow rates are all basically based on calibrations, I must check it. So, this could be errors from there. Reagent addition control, quantity and quality. Suppose a flotation process, I want to add say 5 milligram per ton of material or 5 gram per ton of material, but I am measuring 5 gram, when I am transferring maybe there is some losses somewhere, and maybe I am at the rate at what it should be fed, it is basically fed at a different rate. So, then my chemistry changes, then my entire process sensitivity changes. Okay. This could be the poor housekeeping issues, lots of dirt are there, you are not cleaning the floors. So, what will happen when there is a small breach comes, this dust may get into your flotation tanks, and then my entire chemistry changes and your responses are different. So, you have to have good housekeeping also, not only for safety purposes, but for performance consistency also. Equipment malfunctions, there is some problem with the equipment, I can get that. So, this mass balancing will tell me that where it is going there, and that is why the modern plants, we have got basically sensors, we have got instrumentations for measurement at different nodes, and that basically sends me the numbers in my control room, and I am looking at my control panel, I am looking at that, okay, here there should be 1.08% of copper, now I am getting say actually 0.38% copper. So, that means there must be something wrong somewhere. What would be the reasons, then I know that what are the actions I have to take. So, if you have more of that, is what you call it the process controls, the instrumentation, that is your sophisticated plant, when we say that is nothing but your online measurement systems, how strong is your basically the instrumentation purposes, that is what I said at the beginning, that you bring instrumentation people, you bring electronics people, I can also give problems, and these are basically the say actually such very much wanted by the mineral processing industry. Okay. So, these are the technologies domain you can work with. Planned maintenance interruptions, that is we had a maintenance schedule, but because of some reason, there is some political reason that why we could not do it, there is some strikes by the people, then your maintenance schedule gets disrupted. There is some visit by some senior people, the topmost people. So, what do we say, okay, maintenance बाद में होगा, साहब को plant चलने में वो तो दिखाना है, उस दिन मेरा maintenance का था, उस दिन मेरा chairman आ रहा है, so हम क्या करते हैं, we do not show him that it is under maintenance, we say that it should be running, then your schedule gets changed, and then you may have disruptions into your basically process parameters, Then temperature and pressure changes, that is very common again with the seasonal variations. When the temperature changes, your fluid viscosity and your density, they all changes, and your chemistry changes, and mostly the chemical based processes like flotation, they are very sensitive with this. So, your performances could be different. Moisture content changes, when the temperature changes, your moisture percentage changes, okay. With the variations of your relative humidity and all sorts of problems are there. Then metallurgical balances, the analytical errors could be sampling errors, sample preparation errors, we have all discussed this, assay errors, human communication errors, like say suppose these days mostly these are online, even say suppose I am the general manager and I am sitting at my home and I just rang up my process manager, what is the grade of copper in tailings? He told me over phone that it's 0.089 and I heard that it is 1.089, then I start blasting at him, kya kar rahe ho, kuch nahi kar rahe ho, but it is basically the, so now these days what is happening, it is basically you can have online systems, you know, to monitor that. That is what these IT sectors and all this, they are basically helping us, okay. So then your weighing errors, maybe from your balances they are not calibrated. So even 1% in weighing errors, and when you are dealing with 25,000 tons, so 1% plays havoc, okay, your entire mass balancing changes. Noisy data errors, unstable process errors, time delay errors, particle size errors. So I have to know all these errors. So metallurgical balances, these are all basically discussed, that minimize the impact of errors. How we can minimize? That is, minimize the sampling error, minimize the assay error, okay, and what we can do, that different labs may produce different edges. That is what your weighted average, that calculations I have shown. That is, you send the same sample to 5 different labs, you may get different values, but which value I have to take? I should do some statistics and can get those values and first check that which one is the outlier and which one is basically the data I should take. Minimize the impact of errors, that is sample preparation for the assay lab, samples must be filtered and dried and recovered, that is I am taking based on percentage I am calculating. I am assuming that my material is 100% dry, but if I have 5% moisture in that, so I am also weighing that material with 5% moisture, so my percentage will be changed. So I must ensure that when I am saying that it is moisture free basis, dry basis, it should be dry, okay. Otherwise that is what I say, that is this type of problems are there. Then human communications, mistakes on where sample is taken, mistakes on how sample is prepared, mistakes in reporting ledgers, rush samples can lead to poor quality, you are in a hurry to send this and you commit mistake, okay. So this is what I wanted to basically communicate to you about mass balancing things. Anything else you need to know? But it is a very vast subject, you have to have good grasp in statistics in doing mass balancing. But simple mass balancing for laboratory scale studies, we can always apply these formulas. So this will help you in basically the optimization at your laboratory level, but for plant level mass balancing we need to go to the higher level. It is not possible. Any question?